Hi guys, welcome back to the channel. In a previous video, we have seen that the magnetization along z-axis can be turned perpendicular when we apply an RF pulse. If you haven't seen that video yet, you can click the link which is popping up from here. In this video, we are going to see how this RF pulse helps to turn our magnetization. So let's get into our topic. Initially, we all know at thermal equilibrium, our magnetization will be present along the z-axis. If we want to turn this B naught, we have to switch off the magnetic field along the z-axis and establish one that is perpendicular to the initial B naught. So that the spins which we are precising initially along the z-axis will now start to precise along the new xy axis. As a result, our net magnetic moment turns from z-axis to xy axis. Looks so simple, right? But unfortunately, it is not the case. Remember that the main B naught, which is supplied by a powerful superconducting magnet. Hence, there is no way that this can be switched off, and at the same instant, we get a magnetic field perpendicular to the initial one. We will need to find another approach, and it turns out the key is to use the idea of resonance. The idea is to supply a very small magnetic field along the x-axis, but one which is oscillating at or near the Larmor frequency, that is resonant with the Larmor frequency, the frequency with which the spins precise. Our next question will be, how can a small magnetic field could overcome a strong magnetic field? To understand this, I'm in a position to introduce the idea of the rotating frame of reference. When we apply the RF pulse to the coil surrounding the NMR tube, we are introducing an oscillating current. This oscillating current creates an oscillating magnetic field along the x direction. So similar to the electromagnetic field, the resulting field we call it as RF field. This oscillating magnetic field goes back and forth along the x-axis with a frequency omega RF called transmitter frequency. Remember, this is equal to Larmor frequency as we want resonance. But we know B naught in the positive x-axis will have a negative gyromagnetic ratio and negative Larmor frequency and will rotate along anti-clockwise direction, and that is in the negative axis will have positive Larmor frequency and will rotate along clockwise direction, and it is a lot easier to visualize what is going on. If you don't know how, watch my Larmor frequency video to get a clear-cut idea. Click the link that is popping out from the top. The oscillating magnetic field can be split into two counter fields, B1 positive and B1 negative. That is magnetic field along the positive x-axis and the one along the negative x-axis. Both fields combine together to give a total magnetization. At time 0, they are both aligned along x-axis and so add up to give a total field of 2B1 along x-axis. As time proceeds, both counter fields rotate in opposite direction and combine together to give smaller value of magnetization compared to before. When they are both along the y-axis, there is no contribution along the x-axis and magnetization along x-axis will be 0. And as time proceeds, magnetization will be along negative x-axis. If we represent this magnetization in a graph, then initially our magnetization will be 2B1 along x-axis, and as time proceeds, it will decrease, go to 0, and then proceed along the negative x-axis. This is the graphical representation of our magnetization. And now the mathematical trick we are going to apply, the rotating frame of reference. Consider the xy axis static frame of reference in which the magnetic fields rotate. Take a rotating frame of reference, that is a frame of reference which rather being static is going to rotate. The frame of reference itself is going to rotate. The static frame of reference, we call it as laboratory frame of reference, and the one which is rotating, we call it as rotating frame of reference. The counter fields which are encountered from the rotating frame of reference, which are seen from the rotating frame of reference, even though they are rotating in the laboratory frame of reference, our rotating frame of reference is also rotating. So the counter fields which are seen from the rotating frame of reference will appear static. They are rotating in the laboratory frame of reference. Rotating frame of reference is also rotating. So these counter fields will remain static when seen from the rotating frame of reference. So this magnetic fields, this counter fields will rotate with a frequency omega naught, that is omega RF, which is equal to omega naught. And the rotating frame of reference will rotate with omega rotating frame. The difference between these two, we call it as offset or capital omega. Omega naught minus omega rotating frame. So this omega naught minus omega rotating frame will give nothing but the difference between the magnetic fields, as omega is minus gamma b naught. Capital omega will be minus gamma del b naught of rotating fields and b naught of rotating frame of reference. So with this, we will get del B naught is minus offset divided by gyromagnetic ratio. The del B naught, we call it as a reduced field. Imagine taking this rotating frame of reference frequency equal to the Larmor frequency omega naught. Then the offset will become omega naught minus omega naught, which is 0. Then our reduced field will become 0.
In our case, the rotating frame of reference is nothing but the spins precessing along the z-axis.
The oscillating magnetic field which we apply along x-axis is resonant with the z-axis main magnetic field. So there is no reduced magnetic field. As our offset is 0, there is no reduced magnetic field. Del B naught is 0. Hence, as a result, the magnetic field along z-axis will start decreasing and comes back to the xy axis. Feels so great, right? More similar to the butterfly effect. The small changes which we make will have a bigger impact in our life. So that's it for today, guys. If you like this video, please like, share, comment, subscribe, hit the bell icon, and I will see you guys in the next one. Thank you.